Introduction to the most recent discoveries within the shadow of Geneva. Beneath the surface of our world exists a masterpiece of human imagination, and a potential precursor to destruction. This is the Large Hadron Collider, LHC, an apparatus that serves as an unparalleled tool for experts, enabling them to conduct research into subatomic particles and uncover the enigmatic God particle. The renowned physicist Brian Cox has offered a chilling explanation that has sparked conflicting feelings among scientists, urging them to investigate the fundamental components of matter and scrutinize the very essence of spacetime. However, the immense energies involved in these experiments also pose significant dangers, both recognized and unrecognized. One of the most pressing issues surrounding the way the Massive Hadron Collider works is the potential generation of miniature black holes or other extraordinary phenomena that could yield unpredictable outcomes. While theoretical models suggest that any such black holes would be fleeting and pose no threat to Earth or its inhabitants, the risk of inadvertently creating horrors beyond our control remains unsettling. Furthermore, the vast scale and intricacy of the experiments carried out at the collider necessitate rigorous safety protocols and oversight to mitigate possible hazards. The international community of researchers and scientists involved in the collider's operation is keenly aware of the necessity to prioritize safety and ensure that all experiments are performed with the highest degree of caution and responsibility. The Large Hadron Collider, with its ability to astound and challenge our perception of the world around us, is not merely a triumph of modern engineering, it is also an important hub of contemporary particle physics and cosmology. Its primary goal is to investigate the fundamental particles that constitute the universe, carrying profound implications for our understanding of existence. The LHC allows scientists to replicate conditions just moments after the Big Bang, offering a remarkable opportunity to study the Higgs boson and other essential particles. The Higgs boson, often termed the God particle, was postulated in 1964 by Peter Higgs and colleagues as a vital element of the Standard Model of particle physics. This model delineates the fundamental forces and particles that compose the universe. The identification of the Higgs boson at the LHC in 2012 validated the existence of the Higgs field, an invisible field that imparts mass to other particles. This finding marked a significant achievement, confirming decades of theoretical exploration and enhancing our comprehension of the universe's hidden structure. Nevertheless, like all major scientific pursuits, the quest for knowledge at the LHC is not devoid of potential risks and ethical dilemmas. The energies involved in particle collisions at the LHC are staggering, and the potential for the development of novel forms of matter or instigating unforeseen reactions cannot be entirely dismissed. Some scientists have speculated about scenarios where high-energy collisions could create small black holes or other exotic particles, raising alarms about the potential consequences of such occurrences. While the majority of experts deem these risks to be extremely remote, the very essence of scientific inquiry entails venturing into the unknown. The assertion by Brian Cox, emphasizing the possibility of creating a miniature Big Bang within the LHC, underscores the immense significance and possible dangers of this research. The Large Hadron Collider stands as the embodiment of the zenith of contemporary scientific endeavors. However, its extraordinary capabilities also provoke fundamental discussions about the limits and responsibilities of scientific exploration. The collider, through both its structure and function, seeks to address fundamental questions regarding the universe. Yet, it operates at the margins of human comprehension and technological proficiency. This intersection provokes substantial inquiries about the nature of science, scientific risk, and the ethical ramifications of such advanced research. One of the most exhilarating aspects of the LHC is its capacity to simulate conditions immediately following the Big Bang, providing captivating insight into the early universe. This replication makes it possible for scientists to investigate the particles that existed during the universe's earliest phases, occurrences that would otherwise be impossible to access. By recreating these extreme conditions, researchers can evaluate theories, test predictions, and refine models of particle physics. For instance, experiments at the LHC have the ability to examine the properties of hypothetical dark matter particles, which are believed to constitute a substantial portion of the universe's mass but remain elusive to direct detection. The pursuit of understanding dark matter is propelled by its profound implications for our comprehension of the universe. Currently, dark matter is inferred from its gravitational effects on visible matter, but direct detection remains problematic. The LHC's experiments aim to tackle this challenge by attempting to generate dark matter particles in the laboratory. If successful, this could revolutionize our grasp of the universe and potentially lead to groundbreaking discoveries. Advancements like these shed light on the LHC's role as not just a scientific instrument, but also a catalyst for transformative discoveries that could reshape our worldview. Another captivating area of inquiry involves the strong force, one of the four fundamental forces of nature. The strong force binds protons and neutrons within atomic nuclei, and comprehending its behavior at elevated energies can yield insights into the fundamental structure of matter. The LHC's ability to investigate strong force interactions on an extreme scale enables scientists to explore the dynamics between quarks and gluons, the fundamental particles that mediate the strong force. These investigations could lead to a deeper understanding of nuclear physics and the forces that control atomic and technological behavior. Progress fueled by the LHC extends far beyond particle physics. The collider's complex systems for detecting and examining particle collisions have sparked innovations in computing, data analysis, and sensor technology. For example, the development of the World Wide Web was originally envisioned as a means for researchers to exchange data from particle physics experiments at CERN. Today, this technology has revolutionized global communication and information sharing. The advancements in computing and data management prompted by the LHC have had a significant impact across various fields, demonstrating how fundamental scientific research can drive technological advancement. However, managing such a powerful instrument necessitates strict safety protocols and ethical considerations. The possibility of unforeseen outcomes, such as the creation of new or unusual particles, requires careful risk assessment. While theoretical models suggest that the likelihood of catastrophe is extremely low, this possibility cannot be entirely ruled out. This uncertainty urges scientists to approach their work with caution and transparency, ensuring that safety measures are robust and that the general public is made aware of the risks and the strategies implemented to mitigate them. Public involvement and comprehension is an essential component of scientific research, especially for projects that could affect. CERN, established in 1954 as the European Organization for Nuclear Research, has evolved into a beacon of global scientific cooperation. Located on the Franco-Swiss border near Geneva, CERN is not only a hub for particle physics but also a symbol of international unity in the pursuit of fundamental truths. Within its underground tunnel, the Large Hadron Collider, protons are accelerated to near-light speeds and smashed together in ultra-high energy collisions, replicating the primordial conditions of the early universe. These collisions generate fleeting, exotic particles that have never before been observed in nature or laboratory, allowing scientists to piece together a deeper understanding of matter's most elusive components. The LHC comprises several major experiments: ATLAS, CMS, ALICE, and LHCb, each with its own unique focus, from the study of high-energy particle collisions to investigations into antimatter and the conditions shortly after the Big Bang. Yet, as awe-inspiring as these endeavors are, they are accompanied by profound philosophical and ethical questions. One of the most controversial and captivating aspects is the theoretical possibility of accessing hidden dimensions. According to certain string theories and models involving extraspatial dimensions, high-energy collisions at the LHC could potentially reveal portals into realities beyond our three-dimensional experience. If validated, this would not only redefine physics but upend our very conception of existence and spacetime. Critics of the LHC's ambitious scope argue that the manipulation of forces and energies on such an unprecedented scale carries a non-negligible risk, however infinitesimal it might seem statistically. Theoretical discussions about vacuum decay, strangelets, and destabilization of the Higgs field, while largely speculative, ignite debates about the responsibilities of scientists when dealing with forces that mimic creation itself. This tension, between discovery and danger, embodies the paradox at the heart of the LHC. On one hand, it allows us to answer some of humanity's oldest questions: what are we made of? Where did we come from? What are the forces that govern everything from the smallest quark to the largest galaxy? On the other hand, it forces us to ask new questions. Should every scientific endeavor be pursued simply because it can be? Who decides the ethical limits of such research? Brian Cox's reflections, suggesting that the LHC has effectively created conditions akin to a miniature Big Bang, challenge both scientists and the public to reckon with the scale of their ambition. If, in the quest to understand the universe, we stumble upon truths that could destabilize it, or at least our place within it, how should we proceed? And still, the collider spins on. Each second, trillions of particles whirl through its vast magnetic arteries, creating bursts of raw data that must be sifted, filtered, and interpreted by an international network of researchers. The computing power required is immense, driving innovations in AI and data analysis that ripple far beyond the confines of theoretical physics. Beyond the technical marvels and existential debates, there lies a more human story: the tale of people who dared to push against the boundaries of the known. The engineers who built the collider's intricate magnetic systems, the data scientists who extract meaning from chaos, the theorists who dream of multiverse and time loops, they are all part of a vast intellectual tapestry woven from the threads of curiosity, courage, and sometimes even fear. In the shadow of Geneva, beneath the Earth, the Large Hadron Collider continues its silent, whirring pursuit of truth. Whether it ultimately delivers a deeper understanding of dark matter, a new fundamental force, or a glimpse into the multiverse, it has already reshaped how we think about the universe and our place within it. The question that remains now is not just what the LHC might discover next, but whether humanity is ready to face the answers it reveals. 1954 is among the world's most prestigious research institutions, comprising 23 member states and a vast network of scientists. The LHC is CERN's flagship initiative, but it is merely one element of a larger system, a system of accelerators and detectors that explore the subatomic domain. The LHC accelerates protons to nearly the speed of light, replicating the energy present at the moment of the Big Bang. The resulting collisions create temperatures millions of times hotter than the Sun's core, with a complex collection of magnets that direct the protons on their journey, while advanced cooling systems maintain the magnets at temperatures colder than outer space. The design of the LHC is an engineering marvel. Operating deep underground and shielded from cosmic radiation, the entire ring is cooled to temperatures below those of the vacuum of space, which is essential for the superconducting magnets to function effectively. Collisions occur at 4 points along the accelerator ring, each corresponding to one of the 4 major particle detectors: ATLAS, CMS, ALICE, and LHCb. These detectors capture the aftermath of collisions, enabling scientists to sift through the debris in search of the elusive Higgs boson, a particle crucial to understanding the universe's structure. The LHC is not just a scientific instrument, it is also a testament to human imagination and ambition. It embodies our quest for knowledge and our desire to comprehend the fundamental forces that shape our universe. Yet, as we push the limits of understanding, we must also consider the questions about morality and existence that arise. The ambition to recreate conditions similar to the Big Bang carries significant responsibilities. Likewise, the pursuit of knowledge ought never to come at the expense of safety. The journey of scientific discovery often involves moments of awe, wonder, and the unknown. The Large Hadron Collider, LHC, serves as a testament to humanity's unyielding curiosity and the drive to unlock the deepest secrets of the universe. Despite its immense potential to reveal the nature of matter, the LHC also calls the cosmic origins into question. The balance between exploration and caution becomes vital as we delve deeper into the microscopic world. It becomes evident that the LHC is not just an engineering marvel but a symbol of the intricate relationship between science and society. CERN's vision extends beyond the LHC with the ongoing effort to explore the unknown realms of physics, such as the quest for a unified theory of everything. While the LHC's experiments focus on particle interactions at unprecedented energy levels, the goal remains to answer some of the most profound questions of existence. How did the universe begin? What are the fundamental forces that govern everything? Could there be other dimensions of existence? These questions, though theoretical, push humanity's scientific boundaries further than ever before, allowing us to dream of solutions that once seemed beyond reach. Yet despite these breakthroughs, the scientific community must continually address ethical concerns. A significant issue involves ensuring that the LHC's discoveries are utilized responsibly. With such groundbreaking potential comes a responsibility to ensure that the knowledge gained from these experiments does not unintentionally harm or lead to unforeseen consequences. As new particles or interactions are uncovered, it is essential that their implications are fully considered and that global governance frameworks are in place to guide the use of this knowledge. The LHC's discoveries could have far-reaching effects on fields beyond physics, including energy, medicine, and technology. For example, advancements in accelerated technology may result in better cancer treatment options, while understanding fundamental particles may help scientists devise more efficient energy systems. Collaboration plays a key role in the future of the LHC. The project involves a global network of scientists, engineers, and researchers from diverse backgrounds and disciplines. This collaborative spirit is essential for the LHC's ongoing success and for addressing the challenges it presents. As we move forward, it will become increasingly important to foster international cooperation in scientific exploration. The LHC exemplifies how nations can work together to advance knowledge for the betterment of humanity, transcending geographical and political limits. In an environment where scientific discovery often occurs at the intersection of disciplines, the exchange of ideas and expertise is crucial for progress. The LHC's role in advancing our understanding of the universe, though profound, is only one part of a larger picture. The experiments conducted at CERN are paving the way for future generations of researchers to take the next step in understanding the forces of nature. As the LHC continues to operate and new discoveries unfold, it will shape the science of the future and continue to challenge our perceptions of reality. As we stand on the edge of new scientific frontiers, it's crucial to remember that our exploration should not only seek knowledge, but also respect the ethical considerations that come with wielding such immense power. The questions we answer today may shape the world for generations to come. Conclusion and final thoughts. In conclusion, the Large Hadron Collider represents the pinnacle of human accomplishment in scientific exploration. Its vast potential to unravel the mysteries of the universe is matched by the substantial risks associated with its operation. As scientists delve deeper into the fabric of reality, it is essential to remain vigilant, ensuring that the quest for understanding is conducted with the utmost responsibility and care. The coming decades will likely see the development of even more advanced accelerators and detection technologies, building upon the LHC's legacy. Projects such as the Future Circular Collider, FCC, are already in conceptual stages, promising even higher energy collisions and deeper insights into dark matter, dark energy, and the fabric of spacetime itself. However, with greater power comes even greater responsibility. As these next-generation tools emerge, the need for robust international ethical standards will become more urgent. The line between scientific progress and potential peril must be navigated with caution, insight, and a strong moral compass. Education and public engagement will also play a crucial role in this evolving landscape. It is imperative that the public not only understands the goals of high-energy physics, but also actively participates in shaping its ethical framework. Transparency, open dialogue, and interdisciplinary cooperation must become foundational pillars of scientific progress. Moreover, the implications of discoveries at the LHC and beyond extend into philosophy and metaphysics. If we uncover evidence of multiverse, quantum consciousness, or unknown dimensions, we may be forced to rethink long-standing concepts of identity, causality, and existence itself. These revelations could challenge our most fundamental beliefs and redefine humanity's place in the cosmos. In this way, the LHC is more than just a tool for discovery, it is a gateway to philosophical awakening. It urges us not only to ask how the universe works, but why it exists at all. Are we mere byproducts of random collisions and quantum fluctuations, or is there an underlying order yet to be revealed? Whatever the answers may be, the journey itself will continue to inspire generations of scientists, thinkers, and dreamers. The LHC is a modern cathedral of inquiry, an enduring symbol of our collective yearning to understand the truth that lies beyond the veil of the visible.